Okay, so we're gonna do the step 2, 2014 question 6. So it's actually probably my favorite question on this exam so far, because it's not a lot of complicated algebraic manipulation, but it's more you need to think, and every step leads to the next one, and you need to think how to use the previous result, and you keep, how did I use the previous result, how did I use the previous result. It's a very nice question. So part 1, or not part 1, but it says you need to, by simplifying this expression, sine r plus a half x minus sine r minus a half x, or otherwise, show that when sine a half x is not equal to 0, that we have this sum of cosines is equal to sine n plus a half x minus sine a half x divided by 2 sine a half x. And so we're going to do it that way, by simplifying the expression. And we're going to use this method, which is the method of differences, which is on the step 2 specification. And it's similar to using partial fractions, and it's the method of differences. So if you can have a read. So we're going to use this method. So I'm going to create a new one. There we go. Okay, so the expression they give us is sine r plus a half x, and the x is in the bracket, minus sine r minus a half x. So first we're gonna use the double angle formula for sine to expand this. So we get sine rx cosine half x plus sine half x cosine rx minus sine rx cosine minus a half x minus sine minus a half x cosine rx. And so we're going to use two identities. We're going to use the fact that cosine minus x equals cosine x. So you can see that by the graph, because it's a symmetrical graph. It's an even function. And the fact that sine is an odd function, so sine x, sine x is equal to minus sine minus x. So we're going to use these two properties to get rid of the negatives. So we have the same first part. So sine rx cos half x plus sine half x cos rx. Then the cosine minus a half x just becomes cosine half x. So we have minus sine rx cosine half x. There we go. And the sine minus a half x becomes, the minus sine minus a half x becomes just sine half x. So plus sine half x cos rx. And so this term cancels with this term. And so we're left with 2 sine half x cosine rx. Okay, so now they want us to use this to rewrite the sum of cosines as sine of n plus a half x minus sine half x over 2 sine a half x. So the first thing we're going to do is we're going to write what we've figured out. So we figured out that sine, so we'll replace the r with n, or we can keep it r. Sine r plus a half x minus sine r minus a half x, so the x is outside the bracket, is equal to 2 sine half x cosine rx. So now we need to be careful. We know that the range, so we're told that sine half x is not equal to 0. Okay, so we can divide by sine half x. So that's good to know. So we're going to do it. So sine r plus a half x minus sine r minus a half x divided by 2 sine half x is equal to cosine rx. So that's nice. And now we're basically done, because we're going to use the method of differences to solve this problem. So we're going to sum. So the left side of our expression was the sum of r equals 1 to n of cosine rx. And so that means that and we know that this, so we can pull out the denominator, 1 over 2 sine half x. Okay, and it's this denominator multiplied by the sum from r equals 1 to n of sine r plus a half x minus sine r minus a half x. And we can actually rewrite this as so no, we don't need to rewrite it. We can just look at a few little terms. So when r equals 1, so we're just going to focus on this part, because we're going to see that it actually cancels. When r equals 1, we have sine of 3 halves x minus sine of a half x. Okay. When r equals 2, we've got sine of 5 halves x minus sine of 3 half x. R equals 3, we've got sine of 7 half x minus sine of 5 half x. And so we notice that this term cancels with this term cancels with this term, and therefore with r equals n, we'll have sine of, n plus a half x minus sine of n minus a half x. But we know that the n minus a half will cancel with the previous term with n plus 1. And so we just, this section here just becomes sine n plus a half x minus this term that was never taken away. So minus sine half x. Okay, and so in total, now we can factor in the denominator. In total, we have that our sum from r equals 1 to n of cosine rx is equal to sine n plus a half x minus sine half x divided by our denominator, which was 2 sine half x. And now we can check that this was indeed the form that we wanted. Sine n plus a half x minus sine half x over 2 sine half x. So it's quite nice how we were able to use. It's always nice when you can use the method of differences to cancel out expressions. So this is quite nice. So now we define a function, s of n, for n positive integers. And it's defined as the sum of 1 divided by r times sine rx. And we're told we want to find the stationary points of s of 2 between 0 and pi, and then sketch the function. Okay, so that's quite easy, just using a little bit of calculus. So firstly, what's S of 2? So S of 2 is sine x plus a half sine 2x. That's S of 2. Now we want to sketch this function. So let's try and find a few points. So we're sketching from 0 to pi. So we're going to find the usual points. So S of 2 of 0, well, that's equal to 0. S of 2 of pi is equal to 0. S of 2 of pi over 2, well, that's a bit more tricky. But we have sine pi over 2, which is 1, plus, oh, no, it's not, it's just equal to 1, so that's easy. Okay, so here we have a few points. So now, so we know already that our function, so if we draw, yeah, so that's 0, minus 1, 1. We know that maybe pi over 2, this is pi. We know that our function is a 0 at pi, a 0 at pi over 2, and is 1 at pi over, is a 0 at 0 and 1 at pi over 2. So now if we differentiate our function to find the turning points, so the derivative is equal to, so the derivative of sine x, which is cos x, plus the derivative of a half sine 2x, which is just cos 2x. Cos 2x. And now, so if we use some trig identities on this, so we know that this is equal to cos x plus cos 2x, so double angle, so it's cos squared x minus sine squared x. However, if we use the fact that sine squared x plus cosine squared x equals 1, we get that our derivative is equal to cosine x plus 2 cosine squared x minus 1. And we can factorize this. So this is equal to 2 cosine x minus 1 times cosine x plus 1. Okay? And so we can find our turning point. So our first turning point is when cosine x equals minus 1. So that's when x equals pi. Our second turning point is when cosine x equals a half, and that's when x equals pi over 3. Okay, so we can go back to our sketch. So we know that we have a turning point here, and a turning point at pi over 3. So pi over 3 is about here. And we want to evaluate, firstly, to have an idea, let's evaluate the function at pi over 3 to see where it is. So if we use a calculator, pi over 3 plus a half of sine 2 pi over 3, we see that it's at about 1.3, so it's somewhere here. And so now we're ready to sketch. So we know that this turning point, we're ready to sketch our function. So our function we know that it goes up. There you go. So sine 2 pi over 3. Then it goes down. Okay, and then it needs to reach the pi, so it'll sort of level off, but never reach a minimum point until it reaches pi, and then, well, then we're not really interested in what happens. We don't need to. So we have a turning point at pi over 3, a turning point at pi, and 4 points that we know. And so that's a good enough sketch. So there we go. This is part 1 of the question done. So now for part 2, we want to show that if our function has a stationary point at x0, where x0 is within our range, then we have this expression, sine of nx0 is equal to 1 minus cosine nx0 tan half x0. Okay, so we're told that Sn of x0, so x0 is a stationary point. Stationary point. So what's a stationary point? Well, a stationary point is a point where the derivative is equal to 0. So we're going to want to calculate the derivative of Sn. Now, Sn of x is equal to the sum of r equals 1 to n of 1 over r cosine, not cosine, sine of rx. So the derivative, therefore, we just need to derive what's inside the sum. So it's still the sum of r equals 1 to n. Or now the derivative of 1 over r sine rx is just cosine rx. So this is our derivative. However, we already have an expression for this. In the first part of the question, we found an expression for this. We found that the sum of cosine rx was equal to sine n plus a half x minus sine half x over 2 sine half x. So I think that's what it was. Yes, so this is equal to the derivative of x. Okay, so what do we have? We're told that at x0, the derivative of 0. So f dash of x0 is equal to, well, it's equal to sine n plus a half x0 minus sine half x0 divided by 2 sine half x0 and is equal to 0. So we can multiply by the denominator, so the denominator cancels. And then we can expand this sine n plus a half, so we get sine n x0 cosine half x0 plus cosine nx0 sine half x0 minus sine half x0 equals 0. So we can rewrite this as sine nx0 cosine half x0. So let me just check. So let's look at the form they want. So they want sine nx0 equals. Okay, so is equal to. So now I can factorize by sine half x0 times 1 minus cosine nx0. So we take this term and this term to the other side, and then we divide by cos half x0, and we're allowed to divide by cos half x0 because where this is between 0 and pi, not inclusive of pi. So cosine half x0 is never equal to 0, so we're allowed to divide by cosine half x0. So we have sine of nx0 is equal to sine of half x0 times 1 minus cosine nx0 over cosine half x0. And sine over cosine is tan. So we have that sine of nx0 is equal to tan half x0 times by 1 minus cosine nx0. There we go. So we've shown that in a stationary point, so for when x is a stationary point, we have this identity that sine nx0 is equal to 1 minus cosine nx0 times tan half x0. So now they want us to prove, so we knew that x0 was a stationary point for Sn. Okay, so, and we want to prove that it's Sn in x0 is bigger than Sn minus 1 in x0. Okay, so to do that, we need to consider wait. Yes. Okay. So what do we need to consider? We need to think about. So what's Sn x0? So we want to show that Sn x0 is greater or equal to Sn minus 1 x0. Okay, but Sn x0, that's equal to Sn minus 1 x0 plus this expression, this tan half x0 1 minus cosine nx0. There we go. So we want to show that this term is greater or equal to 0. So the first thing we look at tan half x0. And we know that 0 is less than x0 is less than pi. So we have 0 is less than half x0 is less than pi over 2. And if we look at a graph of tan, the graph of tan asymptotes like this, where here is pi over 2. So we know that tan of half x0 is greater or equal to 0. It's actually greater than 0. It's greater than 0. Okay, so now the second term is 1 minus, 1 minus cosine nx0. 1 minus cosine nx0. Okay, but again, we know that cosine nx0, well, that's less or equal to 1. And so 1 minus cosine nx0 is greater or equal to 0. Therefore, this term here is greater or equal to 0. And so we have that Sn of x0 is greater or equal to Sn minus 1 of x0. There we go. Okay, so we've shown that Sn of x0, where x0 is a stationary point, is greater or equal to Sn minus 1 of x0. And now we want to deduce that if Sn minus 1 of x is greater than 0 for all x, then so is Sn of x. So this is where we need to think a little bit graphically. So what do we want to show? We want to show that Sn of x is greater than 0, and we're told that Sn of minus 1 of x is greater than 0. And this is 0 less than x less than pi. Okay, so we're given this information. And we're also told from the previous question that if x0 is a stationary point, the stationary point of Sn of x, then we have that Sn of x0 is greater than Sn minus 1 of x0. So this is the information we have. So now we're going to think a little bit graphically. So we still have the fact that in 0 and in pi, our graph is equal to 0. So let's think what would happen if Sn of x0 was not greater than 0 for every point on the interval. That means that there's some point here where it's under this line. And so it means that firstly there'll be a period of the graph where there's a negative gradient, because it needs to, on average, travel down. So therefore, there's obviously going to be a period of the graph where there's a negative gradient. So we have a period of the graph where there's a negative gradient. And then from this point to this point, it needs to travel up. So there's a period of the graph where there's a positive gradient. And because our line is continuous, now obviously the graph could go up and then hit, but I'm just saying that at one point it will go down, and at one point it will go up, and therefore, if this is the x-axis, so at one point it will go down below the x-axis and go up also below the x-axis. And because our graph is continuous, that means that there is a minimum point, a stationary point, below the x-axis, x-axis. So what does this tell us? So this means that there is an Sn of x0 that's less than 0. Okay? But we know that Sn of x0 is greater than S minus 1, Sn minus 1 of x0. And because Sn minus 1 of x is greater than 0 all the time, we know that this is greater than 0. And so by conclusion, this statement here is absurd. It's incorrect, and so Sn of x is greater than 0 for all x in the interval. There we go. So this is question 2 done. And now question 3 is very easy, because we just need to do an induction on n. So we're going to look at S1 of x. So S1 of x is just equal to sine x. And we know that the graph of sine x from 0 to pi is this. So this is pi, this is 0, this is 1. And so we know that S1 of x is greater than 0 for all 0, what's the range? Oh no, okay. It's greater than equal to 0 for 0 less or equal to x less or equal to pi. Okay, so now by induction, we assume that sk of x is greater or equal to 0 for the interval 0 less or equal to x less or equal to pi. And we want to show, we want to show that s of k plus 1 of x is greater or equal to 0 for the interval x pi. But we've already proven. So in the previous question, we proved that if Sn of x. So we proved that if Sn minus 1 of x was greater than 0, this implied that Sn of x is greater than 0. And therefore, the fact that Sk of x is greater or equal to 0, and the or equal to is not a problem in this case, because the only difference is that we're including 0 and pi, but we know that our function is 0 and pi in all cases, so that's not a problem. We know that the fact that Sk of x is greater or equal to 0, using this property, implies that Sk plus 1 of x is greater or equal to 0. And therefore, we can conclude that for all n greater or equal to 1 integers, Sn of x is greater or equal to 0 for the interval 0 less or equal to x less or equal to pi. There we go. So that's the end of the question.